Welcome to solverfy.
Some weak acid, HY, partially dissociates into hydronium ions and Y-, and this forms a buffer. If this buffer has a pH of 8.77, where HY has a concentration of 0.110 molar and Y- has a concentration of 0.220 molar, we can calculate the pKa of HY using the Henderson-Hasselbalch equation. Rearranging this, we get pKa equals pH minus the log of the buffer component concentration ratio. So now we can plug in our values here. This is then equal to 8.77, some minus 0.301, which is 8.47. Now let's say we add 0.0015 moles of barium hydroxide to 0.350 liters of the buffer solution. We can find the concentration of barium hydroxide since molarity is just moles over liters. So 0.0015 moles over 0.350 liters, and we get 0.00429 molar barium hydroxide. This means that we have 0.00429 molar barium and twice as much, so 0.00857 molar hydroxide. This is because there is a 1-to-1 ratio between barium hydroxide and barium, and a 1-to-2 ratio of barium hydroxide to hydroxide. The weak acid, HY, is going to react with the hydroxide ions from the added barium hydroxide to create water and Y-. Hydroxide is a strong base, so this reaction is going to go to completion, which is why there is a single forward-facing arrow. So now we can set up an ice table where initially we have 0.110 molar HY, 0.00857 molar OH-, which is this number here, and 0.220 molar Y-. Liquids aren't included in these calculations, so we can just ignore water here. To find the change, we know that all of the reactants on the left side that can react will, and since hydroxide is the limiting reagent, we know all of it will react. So the change for hydroxide is negative 0.00857 molar, and since there's a 1-to-1 ratio between hydroxide and HY, the same concentration of HY is going to react as OH-. So the change for HY is also negative 0.00857 molar. Then again, since there's a 1-to-1 ratio between hydroxide and Y-, the amount of hydroxide that reacts will form the same amount of Y- on the other side. So the change for Y- is a positive 0.00857 0.857 molar. Then for equilibrium or end, we just add initial and change. So for HY, we have some 0.10143 molar. For hydroxide, we end with 0 molar. And for Y minus, we end with 0.21143 molar. And now that we have these final concentrations for Y minus and HY, we can use them to calculate the pH of the final solution using the Henderson-Hasselbalch equation again. So we can plug in our calculated value of pKa, since that won't change. And then we can plug in our new concentrations that we found in the ice table. So 0.21143 over 0.10143. This is 8.47 plus 0.319, or 8.79. And that's our final pH.